All right, guys, we're going to move into section 7.2, which isn't as long of a section as 7.1, but we're going to break this up into two videos here. Hopefully it's not going to be too bad. All right, so what we're going to get started with, your book kind of tries to do two really separate things in 7.2 that probably could have been two separate sections. The first thing we're going to work on here is this concept of transforming graphs. And what we're going to talk about here at the beginning is how to graph exponential functions like this first example we're going to look at here that are a little bit more complicated than what it was that we dealt with in 7.1. But I'm hoping some of the tricks we're going to talk about are going to sound familiar. Noticeably here, guys, we're going to start with a parent graph that we discussed in 7.1, and that parent graph that we had before was just y equals 2 to the x. So I'm going to draw that here with a dotted line. The important thing we learned in 7.1 is that that graph is going to pass through the point 0, 1. It's going to have a horizontal asymptote here at the x-axis, and it's going to start very, very close to that x-axis. But then it's going to start to increase very, very quickly, increasing at an increasing rate. So what I drew there in in green, is the parent graph here for y equals 2 to the x. But now I'm going to switch back to purple, and we're going to try to graph this particular function right here, y equals -3 times 2 to the x. And what I'm hoping you guys remember here is that the only difference between this graph we're going to do and the parent graph is the presence of that -3 out in front that's being multiplied by 2 to the x power. And just like we did with quadratic functions, which were parabolas, just like we did with all of the other functions that we dealt with in previous chapters, including square roots and cube roots and things like that, what a negative coefficient does, that negative out in front, is it's going to flip this graph over the x-axis. So it's going to move around this way. So I think we can read this, instead of going up from left to right, the way that the green graph did, this one is going to go down. The other thing is the presence of that 3 in front is going to stretch this graph vertically and make it a little bit taller. So what that's really going to do for us, guys, is that our starting point, instead of being right here at the ordered pair 0, 1, is now going to get multiplied by -3. So again, that was the ordered pair 0, 1, but if we multiply that y value by -3, we're actually going to begin this graph right here at 0, -3. I got that by multiplying this 1 by that -3. And if you're not sure, you can always just take this equation right here and just see what happens when you plug in a 0. We would start by taking 2 to the 0 power, and we have to remember that any number to the 0 power is 1, and 1 gets multiplied by -3 to get -3 for our answer. So that point right there, 0, -3, kind of becomes our starting point. And everything else on the graph really works the same way, except now we're flipped below the x-axis instead of being above. And that -3 means this is going to kind of increase a little bit quicker right there, but that's about as much room as I left myself in the graph. So I don't know why I did that one as a dotted line. That should have been solid. So our actual graph here, everybody, is going to look something like this. Okay, so the negative coefficient flipped it over the x-axis. That's why this one goes down instead of up. And that 3 just kind of stretched it out vertically and maybe it a little bit taller, made it get a little farther away from the x-axis than it normally would have. And I just got a couple more graphs with you guys that are variations on that same theme. So let's talk about one that looks like this, where we've got y is equal to 2 to the x plus 3 power and -4. And now I'm hoping you guys remember from previous chapters what it does when you've got numbers that are added or subtracted either directly with the x or at the end of the function. When something is adding or subtracted directly to the x, that is a horizontal shift. That takes us either to the left or to the right. And horizontal shifts are always opposite of what you would think. +3 means that this graph is actually going to move left 3 units compared to its parent graph. The -4, a number added or subtracted at the very end, is a vertical shift. That's going to take you either up or down. And this one is straightforward because that's a -4, that means that this graph is moving down 4 units from its parent graph. So again, none of this is any good to us unless we remember what our parent graph looks like. A parent graph begins at the ordered pair 0, 1, hugs the x-axis as an asymptote, and then increases pretty quickly like that. Now what I'm going to do though, guys, is take this starting point right here and apply these two shifts to that point there. We're going to take the ordered pair, which was located at 0, 1, and we're going to shift it left 3 units, so 1, 2, 3, and then down 1, 2, 3, 4. This point right over here should be our starting point. Now let's just think for a second before we move on at all. That ordered pair right there looks like it has a coordinate of -3 and then also -3 for its y coordinate as well. So let's see if that works. If we put a -3 in here for x, -3 plus 3 is going to get us 0 for the exponent. 2 to the 0 power is 1, and 1 minus 4 gets us the -3 we were looking for. The only other thing I'm going to draw here is the horizontal asymptote, which used to be located right here at the x-axis. That also gets these same two shifts applied to it. That red dotted line is going to move left 3 units and down 4. Well, moving it left 3 doesn't really do anything because it just moves horizontally and it doesn't really have any impact on it. But moving it down 4, 1, 2, 3, 4 units means now that we have a horizontal asymptote at the line y equals -4. And from there, guys, nothing else changes in this graph. There's no flip, there's no stretch. So this is the shape of a normal exponential, oops, sorry about that, of a normal exponential growth curve. And it's just going to look something like this instead. So what we have in purple there is the graph of y equals 2 to the x plus 3 power and then a -4 at the end. So I'm hoping that rings a bell or two for you guys in terms of horizontal and vertical shifts, because this is probably the 3rd or 4th time we've seen this year the same values of h and k making those changes to a parent graph. Okay, how about this one right here, guys? Let's take a look. Now, this one is meant to scare you a little bit right here because some different things are going on right here. We've got y equals 30 times 1/2 to the x power and then a -10. So there's a lot going on right here. I realize, though, with the big numbers that I gave you, the graph that I have right here is really no good to you guys. So I'm actually going to go ahead and just delete that graph right here. If I could figure out how to do that, I'd be all set. There we go. I think I can do that. And we're going to go ahead and we're going to draw our own graph right here. So let me switch to black right here. And if we think about what's going on in this graph, let's take a look at a few different things right now. Normally, our graph would have a horizontal asymptote at the x-axis, but that -10 is going to move everything down 10 units. So I'm going to go down here to -10 on my y-axis, and that is where my horizontal asymptote is going to be now, because everything right here was shifted down 10 units, and that includes the horizontal asymptote. We'll see how that impacts things in just a second. The other thing to talk about right here is the impact that that coefficient out in front, that a value of 30 has. And remember, guys, that is actually the initial value of your function, although this one's a little bit tricky. Let's go ahead, though. I'm getting ahead of myself a little bit. Let's see what happens when we just think about plugging in a 0 into this function. We would start off by taking 1/2 to the 0 power, and again, anything to the 0 power is equal to 1. 1/2 to the 0 is 1, times 30, that gets us 30, but then we're going to subtract 10 from that value, and 0.20 is going to be our initial value. Now, I already don't like the way I set this graph up and where I put everything, because I didn't leave myself enough room right here. But let's see. If I'm trying to get my scaling right here, let's see. If that's -10 on the bottom, positive 20 is maybe up here somewhere. All right, and that tells me that this graph is going to pass through that particular point right there. Now, the other thing that's difficult to notice about this graph, and this is the kind of thing I'm hoping you guys will eventually pick up on, but maybe we don't know yet, is that this b value right here, the base of your exponent, 1/2, is less than 1. And one of the things we said in 7.1 is that if b is less than 1, that means we are dealing with an exponential decay function. This thing isn't going to grow from left to right. It's actually going to go down from left to right. And let's see if we can prove that here just by taking a couple of x values here and plugging in to see what happens. What happens if we put in a 1 for x? We would take 1/2 to the first power, which is 1/2. Multiply that by 30 to get 15, and 15 minus 10 is 5. So the ordered pair 1, 5, I'm just guessing at where this is here, guys, but the ordered pair 1, 5 would be somewhere right about there, and I think you can see already by looking at the 2 purple dots that I have that this function is actually getting smaller from left to right. And I think if I put in anything bigger than that, you're just going to see more of the same. What we could do is put in a number like -1. And what's happening here, guys, is if we take 1/2 to the negative first power, that actually turns into a positive 2. 2 gets multiplied by 30 to make 60, and 60 minus 10 is 50. So we're at -150, which is way the heck up here somewhere, and I'm hoping those 3 purple dots tell you what we need to see, guys. This is a function that is decaying pretty rapidly, but it's going to level off, and it'll never touch its horizontal asymptote, nor will it ever cross it over to the other side. So because the base of this exponent was smaller than 1, which is what we said right here, that makes it an exponential decay function that's going down from left to right. So those are 3 different types of transformations that you're likely to see. If it helps you guys a little bit, this is a table that I took out of the electronic version of the textbook, just kind of a concept summary, it's called right here, for what can happen to an exponential function. So if your parent function is right here, y equals b to the x, and we use 2 most often for that b value, couple of things going on right here. When you've got an a out in front, that's a stretch right here. It says if a is greater than 1, it's a compression if a is less than 1. And then if that's a negative number right here, meaning if a is less than 0, that's when you get a reflection over the x-axis. And then down on the bottom right here, this is what we talked about right here. A horizontal translation is what happens when you have an h value, and a vertical translation is what happens when you have a k value at the end. And you can combine that with an a out in front to kind of put everything all together at once. So a large part of your 7.2 homework, in fact the first part I think, is asking you guys to graph transformed exponential growth and decay functions. Those 3 graphs will hopefully get you through some of those. I'm going to wrap this video up right now, and then we'll come back and we'll do the rest of 7.2 when we introduce an entirely new number in the next video. Good luck, guys.